A crystal laser is a manufacturer of optical components of nonlinear optical crystals, which is located in France. So I want to just go over a few quick facts and figures about the company before we go to the core of the subject. We are the only European nonlinear crystals manufacturer that is the only company in our specialty that grows our materials. We grow materials. That is what you can see here on the left picture. We do optical fabrication and we do also optical assembly. Here we have an assembly made of 2 crystals. Our main markets are in that very nice caption, where you can see here a laser that's used in materials processing. This is a very important outlet for us. Here you can see a part of a DNA chain, which stands for the biophotonic sector. And below we have here a Rafale aircraft, which is French made, by the way, and a satellite. And those 2 pictures are for space and defense, which are also very important to us. So, like I said just before, we specialize in a few materials which are used for harmonics generation, for frequency conversion of solid state near infrared lasers. So here are a few data. So like I said, we manufacture finished products which we ship around the world in a total quantity of more than 10,000 pieces a year. Our customers are in 40 countries over the globe, 130 customers worldwide at the moment, and we have also there's another planet to which we actually ship, obviously not directly our materials, but where our materials or our products are used, and this is Mars. I will mention that a little bit more in a minute. Our production area is 2,500 square meters, which is approximately the same as 25,000 square feet. What is not on the picture here is that we celebrate this year our 30th year in business. I'm not going to talk much about our growth and fab equipment, which you would imagine. Metrology and QA is very important for what I'm going to say in a few minutes. We have, of course, a lot of conventional metrology equipment, Zygo PTI, an optical surface profiler, which is the new view. We have also atomic force microscope. And aside all this, we have also a full range of specific laser testing benches, which are used to make sure that our components actually perform as expected. And now we move over to the first item of this presentation. But before we get started, I wanted to remind you that there's a networking room, which is where I will be expecting you to ask your questions, and I will provide some more input there. I will be hosting that networking room together with my colleague, Ophélie Wagner, and we are really excited to talk to you there in a couple of minutes. So the first material I'm going to talk about is LBO. So here we have some advances to report in terms of crystal growth, manufacture, and coatings. And the trend, as everybody knows, is toward high power UV laser. And the first question is why LBO as a material is used for that type of lasers. Well, it has very nice optical and nonlinear optical features, which make it a great material for harmonics generation. Here's an example of a green laser. And apart from that, LBO also has a very, very good power handling property. Here's the last example. This is what the Institute for Radiation Tools has achieved in a couple of weeks ago. They reported in October 1.4 kilowatts of a pulsed laser in the visible range femtosecond with one of our LBO crystals inside. Now, what happens with high power UV laser? Well, everybody who knows UV lasers knows that what is to expected is this. So actually, there's a decrease of the output power, which is due to a gradual degradation of the optic surface. Not only the LBO itself gets damaged, but every optic that is on the path of the UV beam. So this process is very well known now, and the dynamics are well understood. What I'm going to talk about is what properties are important to alleviate this degradation process, to make it much slower. And what are the key performance indicators that have to be considered to track those features, track those progress, the progress in those areas. The first one is material itself. LBO material is very nice. It has very good features, and what we use as a KPI here is the material absorption. So to measure that absorption, we have what is called in the industry a PCI tool, where actually when we get your crystal, there's a pump beam that heats the crystal up, and at the same time there's a probe beam that is used to generate an interferometry pattern. And then the crystal is moved from one side to the other over that crossing section here. And here's what you get. This is a record of the bulk absorption, and the walls here and here are actually the contribution of the sides of the optical surface. So what we have found out is that to have a low UV absorption of your LBO material, we need to have a very, very low absorption in the infrared. And what we typically measure for, what we typically specify for UV crystals, crystals used to generate UV light, is an absorption in the infrared, which is in the range of 2 ppm per centimeter. Now, there's work in progress currently to use actually a UV pump beam here, not an infrared one, but a UV pump beam to actually measure directly the absorption in the UV range. And that has not been possible up to now because power available is not high enough to generate a proper signal here. The second thing to look at is the surface finish. Surface finish is an obvious must, but the question is how to characterize it effectively. So our answer is quantify and qualify. To quantify the surface finish, we use a roughness measurement, which we do online when we produce crystals. When we polish our crystals, every time we can use our optical profiler, and what we specify, what we usually have for UV crystals, for crystals used in UV applications, is a RMS roughness of 3 angstroms, more or less. And the next thing is is qualify. And here everybody knows that nothing can replace a trained eye. And our specification here is pretty simple: no visible surface defects and a 25 magnification. Last thing is the error coding itself. And here again, question is, what makes for a good coating? What is the KPI to consider here? And again, you will see here an absorption chart where actually the pump wavelength we use is 355 nanometers. And our preferred coating design for UV application has an absorption, a surface absorption, which is as little as a few ppms. Now, this is not enough. Another thing to look at is the actual damage threshold of your coating. The reason is that I spoke previously about a gradual decrease in output power. This is something that most people can live with. Now, everybody wants to prevent a catastrophic failure, and this is where damage threshold actually comes into play. And again, very good figures here. For the best coating design, we report a damage threshold at 355 nanometers, which is as high as 16 joules per square centimeter. And here are some results. Early on, LBO has been identified as a very good material for high power UV. There's been an experiment done by Dr. Menret at CEA in France, who achieved 360 joules of UV with one single shot. And with this, we have addressed since then the needs of industrial players. And here are a few results we achieved in the last 2 years. 28 watts nanosecond, 100 hertz. Another one very recent is 100 watt at femtosecond, femtosecond pulses. And just a couple of weeks ago, we started providing crystal for a 400 watt picosecond laser, again in the UV. And the driving force towards these high power UV lasers is semicon industry. And here, namely, one of the application is the manufacture of flexible displays with organic LEDs. Now, my next topic is RTP for electro-optics. So everybody here is familiar with this two crystal compensating scheme, which requires very precise fabrication and alignment. And the question is why use RTP as an electro-optic material instead of much simpler BBO or lithium niobate pocket cell? Well, the answer is that RTP has been designed to specifically meet the size, weight, and power requirements for portable Q-switch lasers, which are used in the mostly in the defense industry. So here you can see, for example, the halfway voltages to apply on a set of 2 × 10 millimeter long crystals. The specifications we can achieve are pretty nice. We hit more than 25 dB on a 100% basis. Now, what RTP does is it has 2 other advantages. The one is a damage threshold, which is pretty nice, above 10 joules per square centimeter nanosecond, and it is a few times higher than the one of lithium niobate, which again allows to reduce the size. You can reduce the beam size, which in turn reduces the size of the pocket cell and the size of your voltage supply. The other advantage is the extinction ratio, which is good over a broad temperature range. So here's an experiment we did at Crystal Laser, and we recorded the extinction ratio between -50 degrees and +70 degrees C, and the extinction ratio we recorded is between 30 and 40 dBs. So this is why RTP is now widely used within the defense community. But there's another field of application, and this one is space. Space is a place where ultimately what counts is the hands-off reliability of your system. And this has been made possible in the last 10 years thanks to advances in crystal growth, which allowed the material not to suffer any electrochromic damage, any kind of damage when voltage is applied over an extended period of time. And the best evidence is Curiosity, which is running on Mars, which is scouting the surface of the red planet since 2012. And there's another one on its way already, which will land, I think, next year. And our RTP devices are already present on other missions. One is which is on orbit, which is Aeolus. Another one which is EarthCare, which will be launched, I think, next year. And there are other applications which are gaining momentum at the moment. Again, here, defense application, but with wavelength, laser wavelength, which is longer, which is 2 microns here. This is, as everybody recognizes, an illustration of directed infrared countermeasure. But there are also other applications in that wavelength range, and one very nice, which is potential, is wind sensing. A feature which I haven't mentioned is that RTP has virtually no piezoelectric ringing at fast repetition rates, and this makes RTP a very good, an RTP device a very good pulse picker in ultrafast laser. Another application which is pretty trendy at the moment is quantum technologies. Here we speak, for instance, about photon multiplexing. And again, here, fast switching rates are made possible with RTP, and some people even report a multi-megahertz switching rate. And what we do in the meantime is to grow the size of the devices we manufacture. Here we have a device which is 15 millimeters by 15 millimeters, which we made this year. And we expect other applications to be made possible thanks to the increase of the size. Here we have a nice 1 cent coin next to that device, and we expect next time I will present something it will be a €1 coin, at least hopefully. Well, that was it. Again, thank you very much for your attention, and don't forget about the networking room in a few minutes. I will look forward to talking to you then, and well, talk to you soon. Thank you again.